Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will continue our review of probability. Here, we talk about an example where the random variable of interest has a binomial distribution. We will also be using R. Let's begin. So, this is the problem that I would like to solve with you. Okay? So, in this case, what we have is a random sample of 3 entries. And we are assuming independence between entries. Okay? And the random variable of interest is the number of errors detected by the auditor. Okay? So, as you can see, right, we have a sequence of what we call Bernoulli trials, right? Each inspection is a Bernoulli trial because it could result in a success or a failure, where a success, we're going to say that we have a success if an error is detected, and a failure otherwise. Okay. So again, we have a sequence of 3 of those Bernoulli trials, and since we have independence, y, the random variable, the number of errors, has a binomial distribution with parameters n and p. N is going to be 3 and p is the probability of success, right? So let's say that. So y, number of errors detected in a sample of size 3, right? Given the conditions, we have that y has a binomial distribution with parameters n equals 3, and probability of success p is 0.05. Now, let me remind you what the probability mass function of a binomial distribution looks like. So what we're going to have, let me use f to refer to that guy, or, well, we could use p. Let me use p. Probability that y, the random variable, is equal to a particular value, lowercase y, is going to be given by n factorial divided by y factorial times n minus y factorial times p to the power y times 1 minus p to the power n minus y. And we know that y could be 0, 1, 2, up to n, right? And that p is the probability of success, right? Okay. So let's go back to our problem. So we want the distribution for that random variable y. Remember that a probability distribution is just a list of possible outcomes with the corresponding probabilities, right? So in this case, the list of possible outcomes would be if n is equal to 3, we could have 0 errors, 1, 2, or 3. So the distribution of y is just, we need to find these probabilities. The probability that the random variable y is 0, probability that random variable y is 1, probability that random variable y is 2, probability that random variable y is 3. Okay? So we could use that formula, PMF, to find that. Just substitute, right? It would be n factorial would be 3 factorial divided by 0 factorial times 3 minus 0 would be 3 factorial times b, in this case it would be 0.05 to the power 0 times 1 minus 0.05, n is 3, so cube, right? Because then we have n minus, well, 3 minus 0, so 3, right? So in the end, this is the same as 0.95 cube. And let's find that 0.95 cube, right? Okay. And we could do the same with the others. We could plug in here in the expression of the probability mass function, and we could find the remaining 3 values of the distribution of y. But what we're going to be doing instead is using a built-in function, right? R has a function that can help us evaluate that probability mass function. Here we go. So let me use that hashtag that is just going to be a comment. R will ignore what I'm going to be doing next. So I'm just saying that we're going to be doing part A here. So first we said that y could be 0, 1, 2, or 3, and I'm using this function, this R command, C, concatenate. So, and I'm using the equals, I'm using the equals sign to make the assignment. So I'm saving these guys in this object that I labeled just lowercase y. Okay. Now, if we want to evaluate the probability mass function at a particular point, all we have to do is this. So use the function d binom, the number that we're interested in. So for instance, say that we wanted to evaluate at 0, and we need 2 parameters: size, which is our n, the number of trials, and prob, the probability of success for any given trial, in our case 0.05. Okay, so this is the guy that we found by hand first, right? Just plugging in the expression. Okay, now it turns out that we could evaluate more than one value. Okay, we're going to evaluate all of them at the same time. Okay, now remember that one of the properties of a discrete random variable, right, of a distribution of a discrete random variable, is that each of these probabilities must be between 0 and 1. That condition is satisfied, and that if you add them all up, the sum must be equal to 1. And that's the case. Okay, so now let me save those numbers in an object called p.y. Okay, so we have found the probability distribution for y. Okay, let me show you. What we have is p of y. So for the next one, the probability that y equals 1 would be this guy. Y equals 2 would be this guy. And y equals 3 would be this one here. Okay. Okay, so part A is done. We found the distribution of a random variable y. Okay. Now part B. Let's make a graph. Okay. So to make a graph, we're going to use this R command, plot. The syntax is first, you place the numbers that you want to go on the horizontal axis, in this case the values of the random variable y, 0, 1, 2, and 3, and then on the vertical I want the corresponding probabilities. I'm going to use that argument. PCH equals 19 is telling R that I want solid circles. Call blue, I want blue solid circles. Okay, so that's a basic graph of our probability mass function. Perhaps we can do something nicer. So let's try to do something nicer. How about we modify that and we do something like this. If we use type equals h, what R will do is it's going to draw needles. Okay, makes sense? So we have the height at each of those points. Okay, now let's make it look a bit nicer. Let's add some labels. So for instance, for the horizontal axis, how about y? For the vertical axis, and this stands for label for the x-axis, label for the y-axis. This one is going to be the probability of y. Let me add a main title. It's going to be binomial n equals 3, p equals 0.05. Okay. So now if we go back to our graph, we have labels for the horizontal and vertical, and we have a main title. Now I would like to add those points that we had, right? So y, p dot y, pch equals 19, and color, same color, blue. Okay, so that's a graphical representation of the probability mass function of a binomial with parameters n equals 3, p equals 0.05. Okay, so let's do the next part, which is finding the probability that the auditor will detect more than one error, right? So one way of doing that, right, more than one error would be 2, well, yeah, more than one would be 2 or 3. Well, more than one, yeah, so it's going to be 1, 2, or 3, right? So for part B, done, the graph is done, but for the other one, we said that what we want is the probability that y is greater, so more than 1, right? So what we want here is the probability that y is greater than 1, right? So that would be the probability that y equals 2 or 3, right? So another way of finding this, right? Well, let's do it directly. It would be just, hey, we use the binom function at the following values, 2 and 3, size equals 3, probability 0.05, probability of success. Now we do the sum of those guys, and that's a probability of more than one error. That's what we want, right? Another way would be, if you want the probability that y is greater than 1, that is the same as 1 minus the probability that y is less than or equal to 1, okay? The complement. Okay? So, but now what I want you to remember is that this guy here, the probability that y is less than or equal to 1 is the same as the CDF of the random variable y evaluated at 1. Okay? Now it turns out that R can help you evaluate the CDF. There's a built-in function in R that is going to help you evaluate CDF for popular distributions like the binomial. Okay? So if I'm doing this right, if I compute this 1 minus the CDF of a binomial evaluated at 1, I should get the same answer. Okay? So it turns out that the function that you need to evaluate the CDF is p binom. So we want to evaluate the CDF of a binomial at 1. Parameters same as before, size n, 3, probability of success 0.05, right, exactly the same. Okay, so let's summarize. What we did here is we just very quickly reviewed some of the things that we have seen before for a binomial random variable. We talked about the probability mass function of a binomial distribution. We know that the formula looks like this, right? We also along the way played around with R a little bit using the function plot and the function dbinom. Dbinom is going to help us evaluate the probability mass function of a binomial distribution. So using dbinom and the values of our random variable in combination with this R command plot, we created a graphical representation of the probability mass function for our binomial with parameters n and 3, right? And then we also found a few probabilities we were interested in, right? We did it in two different ways, using the binom function, which again is just going to help us evaluate the probability mass function of a binomial, and also using the pbinom function, which is going to help us evaluate the CDF of a binomial distribution. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.